Hi, it's Robin. Just yesterday I was talking to my friend TheFatman, who's back working on a Commodore 64 demo. I've known him for 20 plus years, and he disappeared for about 17, but he's back at it and programming in Turbo Macro Pro again. And he just discovered a funny bug that I don't know if anybody's seen this before. He told me, just try this. Store A 1272 and press return. Did you see what happened? It changed to 1273. Try that again. And also funny, if you hit return on story 1273, it keeps going up until you get to 1280, and that stays put. So it seems any number from 1272 to 1279 gets incremented by 1. This is a decimal number, so it seems like a really bad and obvious bug, but it doesn't seem to happen to many numbers, like common ones like the screen color, they don't do it, or I don't know, what, 646 or 650. Anyway, it only seems to happen to a certain number of decimal numbers. Presumably it only happens to decimal because I think the majority of the time people programming in Turbo Macro Pro are using hexadecimal, and the bug doesn't seem to exist there. So it seems to be a bug in how Turbo Macro Pro does the conversion from decimal into a 16-bit number. So I wonder if this is just a bug in Turbo Macro Pro. I've been using temp since about 1997, but previous to that I was using Turbo Assembler, which is this was based on. I've never totally looked into the history, but apparently Turbo Assembler goes right back to 1985. And actually, I looked to try and find the earliest copy I could of it, and I found here. So this is the earliest copy I could find of it. It's a crack. We'll load it up here. So here we go. Turbo Ass was cracked in 1985. Germans have a funny habit of abbreviating assembler. So here was possibly one of the very first versions of Turbo Assembler by Wolfram Romhild. So in Germany, and this was published by a company called Omicron. So I thought I'd try that. Here, story 1272, and sure enough, the bug is even in this very earliest version. So this is a bug that goes back 34 years, and it isn't just when you use a store A. If you do like load A, it also does it. Anything that takes the 16-bit address in decimal form. So I was really curious about this bug, so I spent all morning doing a disassembly of it. Not a complete disassembly, but digging into it to try to figure out what the bug was. And I believe I found the cause. So we'll just load up Turbo Macro Pro again. I'm not using the RU version this week. There's no point really. I've got my micro IEC SD card reader as usual from Retro Innovations and my Super Snapshot cartridge. So it's sys 32768 to start the assembler. Look at that. I remembered it. Back arrow C to do a cold start. So reset. And I'll freeze the computer with the snapshot button. Press M to shortcut into the monitor. Oh yeah, before I get into that, just a thank you to my friend David, who gave me this Commodore CDTV remote controller. This is a variation on an Amiga, and I actually got the machine from him, the CDTV system, a while ago, but the controller was missing, and years later he finally found it and gave it to me. So thanks, David. See if I can give that a try in a future episode. How many remote controls have a button on them that says Genlock? Eh? That's pretty awesome. Alright, so I'm in the machine code monitor for Super Snapshot. We're going to be disassembling an assembler. Is that ironic? I don't know. So this is a huge program. We're obviously not going to get into how the whole thing works. I narrowed down the problem to the routine that converts a Petsky string of numbers into a 16-bit value. Okay, and that starts at location AB02 So we're going to go through this and narrow down exactly where the bug is happening. This routine is called with the accumulator already loaded with the first digit. So in the case of 1272, there is a Petsky value of 1 in the accumulator. So the first thing that's done is cleared out these values. These are 0-page locations, 39 and 3A, and they're going to be the running accumulator, whereas this string is turned into a hex value, the intermediate results are stored here. So in the accumulator, you set carry and subtract 30 hex, that's 48 decimal. That's where the 0 character is in Petsky. And 1 is at 31 hex, 2 all the way up to 39 hex, which is the Petsky for 9. So subtracting 30 changes the character value into the numerical value from 0 through 9. And if carry is clear, that means that the character isn't a number, it's too small, it's a lower character, or if it's 10 or higher, branch if carry clear is essentially like a branch if less than after subtract, and branch if carry set is a greater than. In either case, it branches away. This isn't a number, this isn't what we're looking for. And then the remaining number from 0 to 9 is stored in this location, A4AF. And now this is the main loop that happens. The whatever value is in 39, right now it's 0, it's going to be the low byte of this accumulator. On repeated loops, it's going to be a bigger number, but it starts off just at 0. We often do repetitive things in code that aren't strictly necessary for other efficiencies. It just makes sense to do the same action over and over again. So we take that low byte and we push it on the stack for later. Then we take the high byte and we store it in A4B0, which is another temporary workspace that we need. Since the 6510 only has 3 registers, only one is actually good for general purpose math, the accumulator. We need other storage locations to juggle everything. So we're going to save that high byte, a copy of it up here, and we'll get to that later. And then we're going to be doing a loop here. Now this next section is going to be looped through 3 times, and that's because the 6510 doesn't have a multiply instruction, but it does have these rotate left instructions, which are equivalent to multiplying in 2. Now when we're converting from decimal to hex, we want to be able to multiply by 10, but since 10 isn't available, we can do a binary shift left 3 times, and that gets you 8, a multiplication of 8. And then you can separately do a single shift, multiply by 2, add those together. 8 plus 2 is 10. So that's what's happening here. We set up a counter for 3 repetitions. We're going to use the X index. And then we rotate left the low byte. And then we rotate left the high byte, and if there is a carry, it goes through from 3.9 into 3A. 6510, we always do low byte first and then high byte after. And we check for an overflow. If the carry is set after the 16-bit rotate, then this number is too large if carry is set, so it branches away to AAFD, which displays the illegal quantity error. And that's going to happen quite a few times during this routine. And we decrement X, and if it's not equal to 0, branch back up to AB1E here. So that's repeated 3 times this section. Then we pull A off the stack, which is the low byte pre-calculation, and we do a single shift on it. So up here is the multiply by 8. Down here is the multiply by 2. The PHP pushes the processor status, including the carry flag, onto the stack, because that's going to be needed later for a bit of math. Then we set up clear carry, and after multiplying by 2, we add in that original number of 0 through 9, and then that gets pushed on the stack in case there's a carry. We'll scroll down a bit here. And then we add with carry this value that's being multiplied by 2, and then the value 0 through 9 is then added in with 39. And sharp-eyed viewers might realize that this is where the bug is. There should be a clear carry here, but there is not. So that's the problem. But we'll keep going through the rest of the routine here. and I'll come back to that. So we add in that value that's being multiplied by 2, 0 through 9 is added, add it to what's already there, store it back in that location, and then we load the high byte of the pre-shifted value and rotate it left, multiply it by 2, and then we check for an overflow for a carry, which would indicate we have a value larger than 16 bits, and that would again do that overflow error. And we pull back the processor status, which contains the carry, just in case, and add that back in. It's an add with carry 0, so all this is doing is either adding 0, or if the carry was set, adding 1 to handle it going from the low byte to the high byte. Again, checking for an overflow, just in case, pulling back the processor status that was from even earlier. Let's see, back up here, after the multiply, adding that to the high byte, again checking for the overflow, and then storing that in the high byte. Okay, so that has multiplied the value by 10. And just to maybe explain this better, I'm going to show this in BASIC. So you have 127, and you want to multiply that by 10. Okay, which of course is 1270. But since 6510 doesn't have a multiply by 10, instead we want to go 127 times 8 and 127 times 2. And those get added together. 1016 plus 254. And there you have your 1270. So that's what's happening. But the problem is here, during the multiply by 2, that can generate a carry, but so can when we add in the next number. It's done here. The next number, again, the number that causes the bug is 1272. What's happening in the code is that the multiplying by 2 is being combined to 254, and the 2 is added in, and 254 plus 2 is 256. Well, that is a 9-bit value. It causes a carry, and that carry is getting put through in the code. Both, it should be only going up into the high byte, but it's accidentally being added to the low byte as well. So that's the problem. So really, the bug can be triggered whenever you have a number that, when multiplied by 2, is very close to 256, just under, but within reach of the next digit from 0, well, obviously 0 doesn't change it, but from 1 through 9, that causes the problem. So we've got 127 times 2. Any value from 2 through 9 will trigger the overflow. And it'll actually happen with 126, 252, so anything from 4 through 9 as the 4th digit following 126. So that is 1264 through 1269, and even 125 is 250, so anything from 6 through 9 will cause the bug. And finally, 124 times 2, anything either 8 or 9 will cause the bug. So I think those are all the combinations that can happen. So what is that? 8 and 6 is 14, 18, 20. So out of 65536 different combinations, 20 are affected by this bug. Oh, actually it's more, because it can happen on a 5-digit number as well. So for example, 12721, so the 2 changed into a 3. So yeah, so actually there's quite a few more. Somebody who really enjoys math can maybe figure out all the combinations that are affected by this bug. So, can this bug be fixed? So if we take a look at it here, here's the bit where we do the multiply by 2, we add in the value from 0 through 9, save the carry for later, but we don't clear the carry before working with the low byte again. So right here, we need to insert a set carry. But since we're not working with source code, all these opcodes are in memory, and we can't just shift them because there's too many dependencies where there's existing memory locations that are jumped or JSR'd to. It would be a great big mess to try and shift that. So what we do in this case is just make a little patch, find some clear memory. So we can do that trick we did before, set up for snapshot in a previous episode. We had done this where we can clear memory, and then if we go into the monitor, we'll take a look at, see how it's all full of BBs? Okay, so we'll just go into we will load temp with a space, and it will load from location 8000. What we're doing right now is just looking for some space to apply a small patch. So once this file has loaded, we'll see where the file ends in memory. When you load from the monitor, by the way, it always shows the starting address, which is 8000, and here's the end, C8OF. Oh, and one other thing, when we're loading this directly in the monitor, we should look at memory location 0, or actually memory location 1. By default, it's 37. This location controls the current memory map in the 64. And when it's 37, that means that the ROMs are switched in, and we actually want to switch those out by changing that to 35. Normally, the basic ROM is located in that area that we were patching, or that we want to patch, in location A000, 8000, as I like to say. Normally that's basic ROM, but when you change this location here to 5, it then shows the RAM underneath, which is part of where Turbo Macro Pro lives. Of course, this doesn't always work. C8OF, let's take a look at memory there. You see how it's full of BBs? Now, some programs may use memory after, like they load up to this location, but then they may use the RAM after that for data, or even for code. They may even render code to RAM, but in this case, it is safe. You can just prove that by using it. So it looks like C810 is a good location to apply our patch. So we'll look at memory again, AB20. Right here is where we want the carry. When we can't patch in the spot, instead we have to just overwrite AB2F, and we're going to do a jump to C810. And because that is 3 bytes long, we've overwritten not only this add carry 39, but we've started to write over this next one. So there's one more byte here. Actually, we can just look at it. AB2E. You see how there's our opcode, but we've kind of wrecked the next line here because we've only used 3 out of 4 bytes. So what we should just do to fix that is at AB32, just do a NOP, no operation. And then we'll have to, in our patch, include both the add carry and the store A to 39, because we've overwritten both of those, as we can see here. Okay, so now what does our patch involve? I'm just going to assemble that at C810. First of all, we're going to put in the missing clear carry, and then the add carry 39, and the store A in 39, and then we just have to return from the subroutine. Take note that this kind of patch works fine, but you can't mess with the stack in your patch For example, if we had tried to include the PHP, when you do a JSR, it pushes the return address onto the stack. So if we were then to include the PHP, the push processor status, in our patch, and then did the RTS, the return from subroutine, it would actually try to jump back to whatever value the PHP pushed on there. So that would obviously cause a crash. So with these sort of patches, you just have to keep them. They can't manipulate the stack well unless you really know what you're doing. Okay, so we've patched it. It depends on the monitor you're using, but on this one, if you use SS, that stands for slow save. And we're just going to call it temp fix, (8), and we're going to save from location, that's device 8, from location 8000 to C8 16. Always include 1 byte past the location you want to save. Whoops. That's the automatic disassembly because I scrolled. Okay, and we'll hit return. Make sure that's saved okay. There it is, temp fix. And we'll try restarting the computer. Powered it right off to make sure. Go back into my directory here. There it is. And we'll load it. By the way, that % is loading the same as (8), (1), which loads the file into memory from the location it was saved at. If you load with just (8), or with a wedge, slash, that loads to the beginning of basic memory, which on the C64 is 0801. But of course, we want this to load to its proper location at 8000 hex. Okay, and we'll go ahead and try to run that. And the moment of truth, store A in 1272. Yay! Store A in 1268. It works. And how about that 721? There. So we've successfully patched it. The 34-year-old bug is fixed. And now TheFatman is free to keep coding his demo. I'm looking forward to that being done. Well, of course, he did figure out ways of working around it. He's pretty smart. But it's still good to have tools that are free, even of semi-obscure bugs like this. All right, thanks for watching. So those of you who stuck around to the end of this episode, I'm starting a Patreon account. Some of you have asked me to start one of those. And actually, I'm between jobs right now. I would love this to be my full-time job. I don't know if that's possible or not, but if you want to support what I'm doing here, please check the link at the bottom for my Patreon account. I'm still deciding what exactly to put on there, but I think for sure I'll have early access. And also to those who are able to donate more, I'll have your name in a scrolling credit screen at the end of each episode, which will be generated by one of my real Commodore 8-bit computers. So if that's something that interests you. Okay, thanks very much for watching, and we'll talk to you next time.